Hi guys, in this video I will go over the DielsAlder reaction. The DielsAlder reaction actually won Nobel Prize in 1950, awarded to two chemists who jointly discovered this reaction and developed it, two chemists by the name of Diels and Alder. Won Nobel Prize because it became a very useful reaction, particularly for carbon-carbon bond formation and ring formation. We will see there. And it really allowed some complex molecules to be synthesized, including natural products, which before this reaction was discovered, there was much more difficulty in making certain types of compounds. Okay. Now this is a dying type reaction. Okay, it is included in the chemistry of dyings handout. And so what we have here is you got to have a dying, and we'll see that the dying can react with an ene. So let's see here. This would be a diene, ene, and then this would be just an alkene, a single ene, a monoene. And these will actually react together to give a cyclohexene. Okay, cyclohex, six-membered ring, but ene. There will be a double bond here. And so all DielsAlder products will at least contain a cyclohexene. Now there may be other substituents on here. There may also be additional double bonds. It may be another one, and so, but if you sort of ignore one, you see the cyclohexene there. Okay, this is called a conjugate addition reaction. More broadly known as a cycloaddition reaction. Cycloaddition. Where does this come from? We're making a cyclic product, and the two are adding together. So cycloaddition is sort of where that comes from, or how we come up with that term. Okay, this is the most simplest DielsAlder reaction. There's no substituents here at all. You've got to have at least a 4-carbon diene. That's 4 carbons, 4, and then you got to have at least a 2-carbon alkene, and that's 2, and so it's a 4 plus 2. If we just count the atoms, and sometimes this is called a 4 plus 2 cycloaddition reaction. And 4 plus 2, if you took math course along the way, equals 6. Yes, very good. And you see that we now have 6 carbons, and it's actually a 6-membered ring. All right, so little math prereq there. 4 plus 2 equals 6. Mechanism. Well, we'll show mechanism down here. The diene here, the alkene is often called the Dynafile. It likes the diene. Things that like dienes are called Dynaphiles. Just like things that like electrons are called electrophiles. This thing reacts with the diene, and thus it's called the Dynafile, and that's the diene. Now the Dynafile can also be an alkyne. But again, it's 4 plus 2. and we get a 6-membered ring there. Now in this case we have an extra pi bond over here, because ultimately this is 3 pi bonds sort of reacting or interacting together, and when the 3 here, you're left with 1 with the alkyne, and that's why you have an extra pi bond in your ring. So mechanism, I'm going to show mechanism up here, then we'll look here. It's going to be the same, except I tend to like to show my arrows starting a little bit differently. This here was pulled from the web. I didn't generate this, but I like it enough to use it. Mechanism. We can look at this sort of the theory here, mechanism. The diene is going to have p orbitals. All right, 1 electron, 1 electron, 1 electron, 1 electron. And we see pi bond here and pi bond here. All right, see that in our diene. Well, another molecule with p orbitals can approach this. And now I'm going to try to draw these, those 4 and these 2, they can line up with each other. Now there's a pi bond here. But ultimately what happens here is these can approach and react, and the n p orbitals start interacting. Now this is not resonance because we have 2 different molecules. But it is sort of a type of conjugation between different molecules. And this is sort of the transition state. And at that point, the electrons sort of reorganize and bonds are made between these 2 N carbons. And so how can we show that another way? Traditionally is to move the electrons. And so let's say, let's see if I can, a little bit there. First off, here there's really no polarity, okay? And in other examples we'll see polarity introduced, and that'll help sort of guide us. But ultimately we can show the mechanism like this. If these 2 electrons break away and go over here and make bond to this carbon, well, electrons have to leave this carbon. If they sort of hinge up and go make bond to this carbon, well, something has to leave this carbon. These electrons, pi electrons, can move in here because, remember, those electrons left. And so what's the result of these arrows? Well, when that hinges over, it makes bond here, but that's going to be a single bond and thus a sigma bond. This hinges up, and so what used to be a double bond becomes single because the electrons move up and make bond to the other carbon, and we make that single or sigma bond there. This pi bond moves down to be between the 2 carbons, the center 2 carbons of the diene. And so you see from the arrow movement that this arrow gives single bond, that arrow gives single bond, but this arrow gives a double bond. And there you go. And it's all just a transition state. There's no intermediate. The 2 reactants approach each other, the electrons start interacting, and they sort of reorganize and through a transition state, and boom, your product. All right, and that's the best we can do in terms of a mechanism. But by the way, when you have a cyclic transition state, that's called a pericyclic reaction. You can look these terms up. Okay, cyclic transition state, and a cycloaddition reaction is a precise example of a pericyclic reaction. There's different types of reactions that have a cyclic transition state. One type is a cycloaddition, and the most famous cycloaddition reaction is the DielsAlder, which involves a diene reacting with a Dynafile. and a 4+2 cycloaddition to give a cyclohexene. Okay, now from the web they showed it a little bit differently. It's just kind of flipped over. They moved this out. I wish they would have tacked the carbon a little bit better. They're making the single bond from this carbon to this carbon, hinging this out. This comes down to make this single bond, but right here these electrons move up to put pi bond here. So hopefully you can see it. You can really start with any arrow of the three. I could have started by moving this one down. It all happens at the same time, either way. So hopefully you see that electron movement. Okay, some of this stuff will be stated along the way. Let's look, okay, this was the simplest. Let's look at when we have substituents here. Actually, the first one does not have substituents. It's the same here. By the way, what's the name of this simplest diene? Conjugated diene? That would be 1,3-buta, 4 carbons, diene. Is that right? Yep, it's written right there. With ethine, oh, that's here, that's ethine. Up here it's reacting with ethene. Yikes. Ethene. Okay, sorry. I wrote the name here for this guy here. Up here it's reacting with ethene. And sometimes you'll hear the ethene called ethylene with a L in there. Ethylene. Okay. All right. So 1,3-butadiene. Need to realize here that it can rotate. This bond's a single bond and can rotate, although someone could make an argument of why it may not. I'd be open to that argument. But ultimately it can. Because of that, there's sort of two conformations that can exist. The double bonds can sort of both be on the same side of that single bond. Or if you look at the single bond here, one double bond could be on one side and the other double bond could be on the other side. This is called S-trans. About the single bond, the alkenes are trans. This is a conformation. It's not stuck, it can rotate. This would be called S-cis. Okay, here's your single bond. Double bonds are on the same side of the single bond. S-cis. Well, guess what? Since the two N carbons are reacting over here with your alkene, they have to be on the same side. And so the S-cis form is required for the DielsAlder reaction. All right? So that's important to know. And so as this thing is sort of in equilibrium, you know, one conformer it can't react. So only this conformer can. Okay, here's some examples of other dienes. We can of course have maybe a methyl here and it's no longer symmetrical. We'll talk about that. But you can also have dienes that are in rings themselves. Okay, like cyclohexadiene, cyclopentadiene. These actually react pretty fast, relatively fast in the DielsAlder reaction because they're stuck in the S-cis conformation. All right. If you look at this, the double bonds are both on the same side of the single bond that they're connected to, and that cannot rotate like this guy can because it's stuck in the ring. This connects everything. Because they're stuck in this conformation, they're actually more reactive in the DielsAlder reaction. Because think about it, over here, this compound, half the time, it may be hanging out in a conformation that won't react. All right? This compound's always ready to go. This compound too. Now, you got to be careful. Point this out, that you're not always going to see your dienes drawn like this. Okay? Sometimes they may be drawn like this. Now here, if you want to turn this, it doesn't matter how you kind of connect these. That's ugly. That's ugly. Boom, 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 boom. I'll put the loose double bond in the middle, and then we can connect these like this. That's the 5-membered ring sort of turned. It's basically, the 5-membered ring is if you connected over here these two carbons, N carbons, with one carbon. So it's just shown here, not turned like this. But it's still a diene, and dienes can react in these reactions. Okay, so now let's look at the Dynafile, which typically is just the alkene. But most of the time your Dynafile is going to have a substituent on it, and it's usually going to be an electron withdrawing group. Okay? So here's your alkene, but it has bonded to it, in this case, a ketone. And in this case, the cyano group, or nitrile. In this case, esters, and we have two esters. Each carbon of the alkene has an ester. Of course, that's a condensed structure there, condensed down to look like formula a bit. And in this case, this can be trans alkene, or this can be cis, yeah? The alkene, your Dynafile, can also be a ring itself. All right? So when you look at this, you just really want to see the alkene. And the rest is just there along for the ride. Of course, as we said on the previous page, your Dynafile can also be an alkyne. And in this example, the alkyne, each carbon has an ester bonded to it. Now, turns out that having the electron withdrawing group on the Dynafile makes it more reactive because it polarizes the alkene. All these electron withdrawing groups are going to have a heteroatom which pulls electrons away from the alkene. Of course, this is a cyano group, carbon triple bond N, and so we have dipole towards the nitrogen. These are carbonyl groups. You could draw these out. It's carbonyl with an oxygen here, but it's still carbonyl groups. We see carbonyl groups here. There's two of them, and there's two of them here. So pulling electrons away, withdrawing electrons from the alkene. Now, we'll talk more about the consequence of this a little bit later. Okay, let's sort of advance this a little bit towards more sophisticated compounds, and let's look at some stereochemistry. The DielsAlder is known to be a very stereoselective reaction because there's no intermediate. All right? It's just a transition state. The two pi systems approach each other and bam, the cyclohexene is formed. Thus, the original stereochemistry is going to remain intact. The molecules do not have any opportunity to change their stereochemistry. For example, if we zip these two together, and this is 4 plus 2, and of course, again, that equals 6. Here's your 6-membered cyclohexene, remember, we make. We can zip these together like this. Here's your product. But we're going to have these two ester groups. Well, they're cis here. And they're going to be cis in the product. Here, they're cis because the alkene is stereogenic. Here on a ring, they're cis, and they have the same projections. These two carbons now are tetrahedral. It can either be forward or back, and that's the ring stereochemistry that we've talked about several times. But the stereochemistry is maintained, cis product. On the other hand, if your Dynafile here is the trans version, zip these together, still zip together the same way. By the way, it may look like this group is going to be in the way, but not really. All that's planar. The other molecule is really approaching from the top. And so if this thumb is here, okay, this thumb is here, it's not approaching from the side and the group gets in the way. It approaches from the top, and that thumb does not get in the way of it approaching from the top. Okay? So, we can still zip it together. And that's going to give our 6-membered ring. Let's draw the 6 there. And the groups will be trans there. So we'll get a trans product. All right. So again, the DielsAlder reaction is going to be very stereospecific. All right. What about the diene? Is there any stereochemistry there that's maintained? And the answer is yes. It's a touch more difficult to see, but we'll sum it up here. If you look at this diene, the two alkenes are both E, which with two substituents we can call this trans. They're both trans. That is, they're the same. Okay, they're both E. We'll do another example here. We zip these together. Boom, boom, boom. 4 plus 2 is 6. Double bond here, but we'll also have a double bond left over here. Hopefully you see that. The two ester groups are still on sp2 carbons, and so there's no stereochemistry here. All that's planar. But these two carbons are tetrahedral now. And these two groups can be cis or trans. Well, it turns out that if your two alkenes are the same, these two will be the same. And that will be cis. Yeah? Okay. Now, if you take an advanced class in organic chemistry, you may look at this reaction, the transition state, closer and see this stereochemistry. We're not going to do that here in the intro course. We're just saying that if these are the same, those are going to be the same. And so that's just a take-home message. Let's go back up here. We didn't talk about enantiomers. Plus enantiomer, is that right? No, that's not right. This product is not chiral. Okay? Plane of symmetry, right? All right, not chiral. But this product is chiral, and you're going to get plus enantiomer. It's going to be trans, but we can also show that dashed and that bolded, and that would be the enantiomer, where both of these are switched. Both enantiomers would be trans, though. Okay. So the reaction is it's stereospecific, yeah, to a degree, but it's not enantioselective. Okay. Going to get both enantiomers. Again, that's a little bit difficult to explain why, other than the difference comes from attacking left hand over right versus right hand over left. But here's another thing to keep in mind. I don't know if we've stated this before. Okay. So this is going to be racemic. You can only get a single enantiomer if there was a single enantiomer over here somewhere, because there's sort of a golden rule. You can't create optical activity out of the blue. Okay? Not optically active. Racemic mixtures are not optically active. Well, the product mixture can't be, because nothing over here, I'll put the T there, optically active. If nothing over here is optically active, nothing over here can be. So if I did this reaction and only got one enantiomer, which would be optically active, I would be getting a Nobel Prize. But that ain't going to happen. All right? So, plus enantiomer there. How about down here? Plus enantiomer? Yes. There's no plane of symmetry here, plus enantiomer. We could show cis with both of them dashed, and that would be the enantiomer of this. Down here, plus enantiomer. No, hold on. I see a plane of symmetry. Plane of symmetry here. Isn't that a plane of symmetry? No. These two have plane of symmetry, so they're achiral. There's no enantiomer. I could draw a mirror image of that, but it would be the same compound, right? Remember that discussion? But this is not a plane of symmetry, because methyl up is not mirrored by methyl up. So it is, you would also have the enantiomer. This note refers to it's pointing to the alkene. What we really should be saying is these two bonds don't have projections, because they're in the plane. All right, it's not forward or back. These are sp2 planar carbons. Only when the carbon is tetrahedral do you have the front and back, because the tetrahedral, two in the plane, one forward, one back. But with an sp2 carbon, everything is in the plane. Okay. So in the end, this stereochemistry can be pretty straightforward. We're not going to go any deeper than sort of looking at here and seeing that we get the same here. Okay. So here's a couple of homework problems. We got to start looking more broadly at this here. What do we have? First off, what is this? Well, that's chloroform, and that's just solvent in this reaction. Because, what else do we have? We have a diene. Yeah? And dienes can react with alkenes. In what type of reaction? Well, a DielsAlder, and that would be a 4. That's your 4-carbon component, and this is your 2-carbon component. All right? The rest here is substituents on your alkene, and of course the alkene at this point we can call it the Dynafile. And we can show these sort of positioned like these were positioned over here. So they're ready to just zip together 4 plus 2 and make your 6. Give that a try. At this point, you sort of see DielsAlder, and it's like, well, what is this? Well, keep in mind that most all reactions are going to be done in some solvent. Okay? It's not an absolute requirement, but in general, there will be a solvent. And I want you to just be used to recognizing solvents and most often solvents are not going to react. They're just to dissolve something. When they do react, we'll point it out, and we'll even give it a name. Okay, here's another down here. What do we have? Diene. Yeah, you see that? It's conjugated diene. Can any diene react in DielsAlder? I don't know that we mentioned that. It needs to be a conjugated diene, right? It is. Of course, if you only got 4 carbons, if you put 2 double bonds in there, they're going to be conjugated, unless you put them next door, and they could be cumulated, if you remember that. But we do have our conjugated 4-carbon diene, and it turns out that each carbon has a phenyl ring attached, and we want to show this in what type of conformation? S-cis type conformation, right? All right. You can do that on your own. We'll look at those in class. Let's move down here. Let's do some examples with rings. We noted that the diene could be a ring. When you have these, I would recommend you just ignore the connecting carbon here, and we see that this is that with this 1 carbon bridge. All right, just ignore it. I could redraw this, react these two, but I'm just going to zip these together. Okay, ignore that carbon if you can, or redraw it without it. Let's do it here. You can redraw it. Just zip them together. 4 plus 2 is 6. Okay, and this is going to give, of course, your cyclohexene. Double bond will be here. Again, you see the mechanism. The cyano group will be here. And if we number these carbons 1, 2, 3, 4, 5, and 6, over here we can number them 1, 2, 3, 4, 5, and 6. What's missing here? The methylene bridge, CH2, and by the way, a CH2 is called a methylene. Okay, where a CH3 is just called a methyl. So the methylene bridge between carbon 1 and 4. All you got to do is just put it back. Connect carbon 1 and 4 with a carbon bridge. Now that's a CH2 there. All right. It may look a little funny. It's a 6-membered ring, but you got a 1 carbon bridge between 1 and 4 because it was there originally. All right. Now, there is some stereochemistry here, but it's nothing that we discussed. We only discussed things that were on sort of the 1 and 4 carbons or the 5 and 6, either these two or those two. We did not discuss 1 compared to 6. All right. Now this bridge has to be on the same side, and sometimes you might see it drawn a little bolded as if it's coming up. It has to be. It's a one carbon linkage. You can't have one bond up and the other bond down and expect them to be connecting to each other at the methylene carbon. That is enough stereochemistry. Yes, this carbon is racemic. You can show it dashed or bold. Everything is racemic. Only if there was another group on 5 could we then say their relative stereochemistry, if those two groups were cis and trans. If there's another group on 5, well, it would start out being either cis or trans over here. If the group was trans to the cyano, they would be trans here. Okay. You can give this one a try here. This is all where the dienes are in rings. This example, the diene is not a ring, but the Dynafile is. All right? But still, you just want to sort of focus in on the 4 and the 2. Zip it together, 4 plus 2 still equals 6. But what's the remainder going to be? I'll let you try that on your own. We'll look at those in class. Okay, let's look now at what's called a RetroDielsAlder reaction. Reverse DielsAlder reaction. By the way, we didn't talk about this. Is this reaction going to be favored by entropy or not? DielsAlder. 4 plus 2 is 6. It's actually not favored by entropy. You're doing an addition reaction. You're bringing two molecules together, okay? That is decreasing randomness. Okay. Actually, the reverse is driven by entropy. If you break this apart into two different molecules, and that's what a RetroDielsAlder is. This cyclohexene can be reversed into the DielsAlder starting materials, the diene and the Dynafile. All right? And entropy-driven reactions can be promoted by heat. Of course, because heat magnifies the entropy term in the Gibbs free energy equation. So if you heat these products, they'll reverse to the starting materials. How can we show this mechanism? I would start with the pi bond, because those are the electrons sort of easiest to move with. I would move them here. Old windshield wiper. The single bond is going to have to break away. Let's move it down here. Well, this single bond is going to have to move away from that carbon. Let's move it over here, those electrons over here, to replace what left from that carbon. And so what does that arrow movement give? Well, I'll draw it from scratch over here. We now have double bond up, single bond down, double bond this way. Again, sometimes I draw my bonds on the outer or the inner. It does not matter. I usually draw them sort of inner. That's why it looks a little ugly, but I won't comment on that any further. Right? Double bond here, single bond here because it moved up to make double bond up there. But these two carbons are no longer bonded to each other, and so we got that carbon is sitting over here. We broke that single bond. Those electrons moved down to between these two carbons. And here we're breaking this single bond, so these are no longer bonded. And we get those two products. Well, that's what I showed there. Okay? So again, if you heat these products too high temperature, they'll break apart by a RetroDielsAlder mechanism, which when you do it, you want to begin with your pi bond and break this apart back to a diene and an alkene. All right. Now, when you heat reactions, that's often called a thermolysis reaction. Well, more than that, lysis. Therm would be heat. Lysis meaning break apart or cleave. We're doing a reaction, we're cleaving something by heating. So this can be called a thermolysis reaction. So for another homework problem, provide the product of the following thermolysis reaction. All right. And again, what do I see? I see a cyclohexene. Cyclohexenes are made by DielsAlder reactions. Can a cyclohexene break apart back to the DielsAlder starting materials? Yes, that's what we're saying here. Thinking about it mechanistically, I would recommend starting with the pi bond. Okay, give it a try. Okay, we'll end there with this handout. I will show a couple of miscellaneous things about DielsAlder. This is a drug synthesis of Tamiflu, which is used to treat the flu. It's a pretty complex synthesis. Here's Tamiflu here, compound 1. But it begins with a DielsAlder reaction. Now, they're including a catalyst, zinc chloride. We are not going to discuss that. It helps polarize things a little bit better. They're getting a product here. We're not going to talk about the endo-exo. That's sort of when we did this here. I could have mentioned endo-exo, but we don't need to get into that. Not at this level. Okay. The main thing you want to see here is, did they produce a cyclohexene? Also, how did we get this oxygen bridge? Okay. Think about that. Down the road, we'll see tosylates and also mesylates. Okay, and they have a mesylate here, so I'm just pointing this out so you can see this down the road when you look back at this handout. Most of the other reactions here are pretty advanced, but some interesting chemistry. And if you continue on to more advanced organic courses, you may see some of this chemistry. See what else we have here. On the back of the handout here, a biological example of a cycloaddition reaction is in the synthesis of prostaglandins. Okay? These compounds are called prostaglandins. They are involved in blood platelet formation, blood clotting. They help promote that. They're also involved in some inflammatory responses and also perhaps in pain, production of pain, but inflammation, yeah. Inflammation and blood clotting. And a drug that we use to treat both of these things is aspirin. Aspirin is an anti-inflammatory. It will also act as a blood thinner. It will inhibit blood clotting. How does aspirin work? Aspirin and similar drugs work by inhibiting the COX enzyme. What does the COX enzyme do? It converts arachidonic acid, which is a compound that you have in your body. I'm pretty sure it comes from food. originally from food, and then your body maybe can transform and produce arachidonic acid from food sources. Starting point here, and it reacts with oxygen. Okay. Oxygen we can show as a double bonded structure. And this is somewhat like a DielsAlder, but not exactly. One reason being the diene that reacts is not conjugated. But what happens is we can move these electrons. If these sort of flip out, attack the oxygen, these sort of come here, and then these electrons move to go up and make a bond to replace the electrons that left up there. This is a single transition state which leads to a ring, and so it's a pericyclic reaction, but it's also two molecules adding together to make a ring, and it's called a cycloaddition. Not exactly a DielsAlder though. But it does involve these p orbitals sort of interacting, and it's a single transition state. And that leads to, if you can follow the arrow movement, it leads to this structure, which is called a endoperoxide. Two oxygens bonded together is a peroxide, an endoperoxide here. But this reaction requires oxygen, so that's one reason we have to make sure we breathe, okay, to get oxygen for many reasons. But it's also catalyzed and promoted by the COX enzyme, the cyclooxygenase enzyme. And if we inhibit the enzyme, we'll stop this conversion. And if you stop arachidonic acid from being converted to this structure, you're effectively stopping the synthesis of prostaglandins, and thus you can reduce inflammation, because prostaglandins sort of promote inflammation. And they promote blood clotting. All right. So, usually drugs, very often drugs will target an enzyme and block it and keep it from doing something. So, sort of, it's not a DielsAlder, but it's somewhat close, and it's a biological application. You may see prostaglandins in an advanced biology course, or maybe even in biochemistry. Okay, guys, that is DielsAlder. We will likely discuss this page here in class, where we look at regiochemistry. We looked at stereochemistry, okay? Pretty straightforward. The regiochemistry will be a little bit more involved. Think about this. If these are zipped together, which you're going to get, because in this case, we may need to flip this diene over. If we flip it over, this methoxy group will be up. Okay? Which way is it going to zip together? Think about that. We'll talk about that in class. We'll also be doing the DielsAlder lab, potentially in lab. Some semesters, yes. Some semesters, maybe no. In that lab, there is there's a RetroDielsAlder reaction that takes place first to produce the diene. See, dienes can be produced by a RetroDielsAlder reaction. And then we can react it maybe with some other alkene and go towards another DielsAlder product, not back to the original one. All right? RetroDielsAlder reactions produce dienes and alkenes, yeah, as shown here. Okay, guys. Very important reaction. Nobel Prize 1950. See you soon.